Okay, let's dive right in. We're going to break down a pretty tricky 4-mark probability question from a GCSE paper. By the end of this, you'll see exactly how it's done, step by step, following the official mark scheme. Right, so here's the problem we're going to tackle. It's a classic tournament setup, two semifinals, you've got A versus B and C versus D. Then the winners from each of those go head-to-head in the final. The big question we need to answer is, what is the total probability that player A wins the whole thing? With any wordy problem like this, the very first thing you want to do is just cut through the noise and pull out the hard numbers. So the question gives us 4 key probabilities. A's chance of beating B is 0.6. Against C, it's 0.5. And against D, it's a bit tougher, only 0.3. And finally, we're told the probability of C beating B is 0.2. We need to keep these numbers front and center. Okay, we've got our data. Now we need a game plan. And really, the only way to solve this is to map out every single possible path player A can take to win the whole tournament. So let's start breaking those paths down. It's always a good idea to just stop and ask the most basic question. What actually needs to happen? What are the conditions for player A to be the champion? Well, it really boils down to 2 things that absolutely have to happen. First, player A has got to win their semifinal against B. That's non-negotiable. Step 1. Then, second, they have to win the final. But, and here's the twist, who they play in that final completely depends on who wins the other semifinal. And this, right here, is the absolute core of the problem. Player A can win the final by beating player C, or they can win the final by beating player D. These are 2 totally separate, distinct scenarios. So our job is to calculate the probability of each one of those happening. So let's tackle that first scenario. What's the probability that player A wins the whole tournament specifically by beating player C in the final? But hold on, before we can even think about A winning that final, we have to figure out the chances of that specific matchup, A versus C, even happening in the first place. What needs to go right for them to meet in the final? Well, for that matchup to happen, 2 things have to occur. Player A has to win their semi, which we know is a 0.6 probability, and player C has to win theirs, which is a 0.2 probability. Now, in the world of probability, that word "and" is a huge trigger. It tells you to multiply. So that's what we do, 0.6 times 0.2. And that gives us 0.12. So there's a 12% chance that the final will even be player A versus player C. But we're not done with this scenario, not yet. We know the chance of this final happening is 0.12. Now we have to account for the fact that A must also win that match. And the mark scheme shows us exactly what to do next. We take that 0.12, the chance of the matchup happening, and we multiply it by the probability that A actually wins against C, which the problem told us right at the start is 0.5. And half of 0.12 is, of course, 0.06. So the total probability for our first scenario, A wins the semi, C wins the semi, and A beats C in the final, is 0.06. Okay, 1 path figured out, 1 to go. All right, now for that second path to victory. Let's calculate the probability of the other way this could go down. Player A makes it to the final and ends up beating player D. Now, here's the kind of clever part of the question. It doesn't actually tell us the probability of D beating C, but it doesn't need to. We can figure it out. Since there are only 2 outcomes in that match, either C wins or D wins, their probabilities have to add up to 1. So the chance of D winning is simply 1 minus the chance of C winning. That's 1 minus 0.2, which gives us 0.8. And just like before, for an A versus D final to happen, 2 things have to happen. A must win their semi with a probability of 0.6, and D must win theirs, which we just figured out is 0.8. So we multiply them. 0.6 times 0.8 gives us 0.48. So there's a much higher chance, a 48% chance, that the final will be between A and D. Okay, you know the drill now. For the last step in this scenario, we take the probability of this final happening, our 0.48, and we multiply it by the probability that A actually wins against D, which we know is 0.3. 0.48 times 0.3 gives us 0.144, and that is the total probability for our entire second scenario. Here's a quick but really useful little tip, and it comes straight from the mark scheme. The order you multiply these numbers in doesn't actually matter. You can find the probability of the A versus C matchup happening first and then multiply by A's chance of winning it, or you could group it differently. As you can see, either way, you get the same answer of 0.06. It's just good to know there's some flexibility there. Okay, we've done all the heavy lifting. We've calculated the probabilities for both of player A's paths to victory. Now it's time to put it all together and get that final single answer. So, how do we combine these two scenarios? Well, think about it. Player A can win by beating C, or they can win by beating D. And that word or is our next big trigger. In probability, when you have separate events like this, where it can be one thing or the other, but not both at the same time, you add their probabilities together. So, it's pretty simple now. We take the probability from scenario 1, our 0.06, and we add the probability from scenario 2, our 0.144. And that gives us our final answer, 0.204. So, after all of that, there is a 20.4% chance that player A will win the entire chess tournament. So, let's just zoom out for a second. What are the big takeaways here? The strategy is always to break a complicated problem like this into smaller, more manageable scenarios. And remember the golden rules. And means you multiply, or means you add. And always keep an eye out for those hidden probabilities that you might have to figure out for yourself. And just to leave you with a little something to chew on, how would this all change if a draw were possible in that C versus D match, maybe forcing a tiebreaker? How would that mess with the probabilities we calculated? It's a really great way to test if you've really got a handle on the concepts here.